In part 2 of section 4, we're going to talk about how to solve right triangles using trigonometry. So when we talk about solving a right triangle, what we mean is to find all missing side lengths and angle measures. And to do this, we kind of have to review a couple of theorems that we've talked about previously. First of which being the triangle sum theorem, which says that all angles in a triangle add to 180 degrees. And the second one being the Pythagorean theorem. So a squared plus b squared equals c squared, where a and b are legs of our right triangle and c is the hypotenuse. But in order to solve a right triangle, some information must be given. So we either have to have one side and one angle initially, or two sides. If we don't have that information, it's impossible to solve a right triangle using the information we have. So let's take a look at the one side and one angle case. And we're not going to solve the whole triangle, we're just going to solve for x to find the length of CA. So we have a 42-degree angle and we have our side of length 6. So we have to label the sides we're given. So side CA is opposite of our 42-degree angle, and the side AB is our hypotenuse. So if we remember back to SOHCAHTOA, the ratio that involves the opposite side and the hypotenuse is sine. So we have sine of 42 degrees equals our opposite side x over our hypotenuse 6. We're going to put sine of 42 over 1 so we can cross multiply. And we end up with x equals 6 times the sine of 42. And using our calculator, we end up with x equals 4.01. And always make sure that your calculator is in degree mode before you use it to evaluate anything. Next, we're going to look at the two-side case. And we need to introduce a new function in order to use this case, and that's called arc or inverse trig functions. And I'm going to typically refer to them as inverse trig functions. What they do is they are a function used to find an angle if you know the ratio. And there are three inverse trig functions. We have sine inverse, cosine inverse, and tangent inverse. So that little exponent with the -1, that's the inverse notation. So what these trig functions do is they help us find angle measures. So we're going to take a look at some examples first. So we know the ratio for sine of theta is 3/5. We can use this to find theta by using the inverse trig function. And the inverse trig function you used is based on the trig function you're given. So we're given sine, so we're going to use sine inverse, and we're going to do it to both sides of our function. So sine inverse of sine theta is going to equal sine inverse of 3/5. A sine inverse and a sine cancel, so the left side becomes theta, And sine inverse is a function on your calculator. It should be right above sine. In order to get to it, you typically have to hit second and then sine. And once you plug in 3/5, and then you hit enter, you're going to get that theta equals 36.87 degrees. So when we look at cosine of x equals 1/2, in order to solve for x, we take the inverse function, and because it's a cosine, we'll do cosine inverse of both sides. So cosine inverse of cosine x equals cosine inverse of 1/2. Cosine inverse and cosine cancel. So we're left with x equals, and then when you do cosine inverse of 1/2, you should end up with 60 degrees. And again, cosine inverse is a function on the calculator. You just have to hit second and then cosine. Lastly, we know tangent of theta equals 4.8. In order to solve for theta, we use a tangent inverse of both sides, since tangent is the ratio we're given. So tangent inverse of tangent theta equals tangent inverse of 4.8. Tangent inverse and tangent cancel, so we're left with theta equals, and when you take the tangent inverse of 4.8, you end up with 78.23 degrees. So let's use this in a triangle. So we have our right triangle DEF. We want to solve for theta. So we have to figure out which sides we're given. So we have a side of length 5 and a side of length 12. The side of length 12 is opposite our angle theta, and the side of length 5 is adjacent. So we want to know which trig function involves opposite over adjacent, and that's tangent. So we know tangent of theta has to equal 12 over 5. So in order to solve for theta, we use tangent inverse on both sides. So tangent inverse of tangent theta equals tangent inverse of 12/5. Tangent inverse and tangent cancel. So we're left with theta equals, and once you evaluate tangent of 12/5, you get 67.38 degrees. So let's do a few more examples to find missing angles using inverse trig functions. So we want to find our angle. We have the opposite side of 9 and the adjacent side of 21. So again, we want to use SOHCAHTOA. So opposite over adjacent is tangent. So we'll have tangent of our angle equals 9 over 21. We take the tangent inverse of both sides. And our missing angle ends up being 23.20 degrees. In our next example, we are given the opposite side and the hypotenuse, which is sine. So we have sine of our missing angle equals 40 over 42. We'll take the sine inverse of both sides. And our missing angle equals 72.25 degrees. In our last example, we're given all three of our sides. So it doesn't matter which trig ratio we use. We're given our opposite side, we're given our adjacent side, and we're given the hypotenuse. So I can use sine, cosine, or tangent to solve for that missing angle. We haven't done an example with cosine yet, so I'm going to use cosine. So cosine of our missing angle is going to equal the adjacent side 51 over the hypotenuse 85. So we're going to take the cosine inverse of both sides. And we get that our missing angle equals 53.13 degrees. Now, as long as you set up the trig ratio right for sine or cosine and tangent, they also would have ended up equaling 53.13 degrees. Now let's actually solve some right triangles. So remember, when we solve a right triangle, it's to find all missing side lengths and angle measures. And we're going to use the procedures as we did in the problem before, and we're going to also use the triangle sum and Pythagorean theorems as well. So we have our picture of our right triangle ABC with side lengths A, B, and C and missing angles theta, which we've seen before, and then this B is what we call beta. So in our first example, we are given that theta is 51 degrees and C is 34. So I'm going to go ahead and label that in the picture. So theta is 51 degrees and C is 34. So we want to solve for beta, and we also want to solve for A and B. So it's going to be easiest to solve for beta first, our missing angle, because we know beta plus the 51 degree angle plus our 90 degree angle have to add to 180 degrees. This is the triangle sum theorem. So when we add 51 and 90, we get that beta plus 141 equals 180. We subtract 141 from both sides, and we get that beta equals 39 degrees. When you're solving a right triangle, it's always best to start with the easiest thing to find first, and in this case, that was beta. Now we want to solve for A and B, and we're only going to use the 51 degree angle and C having a length of 34. I'm going to solve for A first. So labeling our sides, A is the opposite side, B is the adjacent side, and then 34 is our hypotenuse. So if I want to solve for A, I'm going to use the opposite side and my hypotenuse, which is sine. So we know sine of 51 equals A over 34. We're going to put sine of 51 over 1 so we can cross multiply, and we get A equals 34 times the sine of 51. Using a calculator, 34 times the sine of 51 is 26.42. We now know 2 of our 3 sides, so we could use the Pythagorean theorem to solve for B. But the problem is we had to round to find A, which means we'll probably have to round again to solve for B, and I want to have the most accurate answers possible. So I'm actually going to use another trig ratio to solve for B. And this time I'm going to use the adjacent side and the hypotenuse. So we're going to use cosine. So cosine of 51 equals our adjacent side, B, over our hypotenuse, 34. Put cosine of 51 over 1. So when we cross multiply, we get B equals 34 times the cosine of 51. So when we evaluate that using a calculator, we get that B equals 21.40. And we may have gotten the same thing if we used the Pythagorean theorem. We may not have, but we would have gotten something close if not. But it's always best to go with the most accurate route. So in our last example, we're given that A equals 5.3 and C equals 9.8. So I'm going to erase what I've labeled in the triangle. And plug in our new information. So A is 5.3 and C is 9.8. In this example, it's going to be easiest to solve for side length B first. We're given 2 out of the 3 sides in a right triangle, so the way we solve for the missing third side is the Pythagorean theorem. So we're going to have 5.3 squared plus B squared equals 9.8 squared. So when we square 5.3, we end up with 28.09 plus B squared equals 96.04. Subtract 28.09 from both sides, and we get that B squared equals 67.95. Now to solve for B, we're going to take the square root of both sides. And because we have only rounded 1 decimal place for A and C, I'm going to do the same thing for B. So to 1 decimal place, B is 8.2. Now we want to solve for theta or beta. It doesn't matter which angle we solve for first, and I'm going to solve for theta. So if we look back at our picture, we want to use our sides of A and C. So from theta, A is the opposite side and C is our hypotenuse, and the ratio that involves opposite and hypotenuse is sine. So we have that sine of theta is going to equal 5.3 over 9.8. Now to solve for theta, we're going to use an inverse trig function. So we're going to do sine inverse of both sides. And we end up with theta equals 32.74 degrees. We could use a inverse trig function to solve for beta, but the triangle sum theorem can also be used here. Because all we have to do is add the angles together and set them equal to 180. I don't have to square anything. We can use that beta plus 32.74 plus 90 equals 180. It's just as easy to use the triangle sum theorem. So 90 plus 32.74 is going to give us 122.74. We're going to subtract 122.74 from both sides, and we get beta equals 57.26 degrees. Now if I'd used an inverse trig function like cosine here, I still would have gotten the same measure for beta. So as you're working on the assignment for solving right triangles, let me know if you have any questions on inverse trig functions or setting up your trig ratio.